Hi, my name is Elise, and this is my remote sensing project video. The goal of this project is to create a 3D model of a target of interest on the University of Maryland campus. This was to be done by creating and deploying a Lidar sensor that could collect 3D measurements of the target. Those measurements would first be combined to make a 3D point cloud and then turned into a 3D mesh of the target. The end goal of this project is that by combining all the different students' work, we can slowly build a 3D mapping of the UMD campus. So what is remote sensing? Remote sensing is gathering information about your environment without having a sensor in physical contact with that environment that you are measuring. There are many different types of remote sensing technologies, for example Lidar, the type we're using for this project, taking pictures with your camera, submarine sonars, weather radars, and many more. All these sensors can be categorized as either active sensors or passive sensors. Active sensors are actively transmitting electromagnetic radiation and then collecting it back off of the target. This is how sensors such as Lidar and radar operate. Passive sensors are passively receiving naturally occurring electromagnetic radiation. For example, when you take a picture outside and the camera is receiving the light from the sun. The two main subsets of remote sensing used in this project are Lidar and computer vision. Lidar stands for light detection and ranging, and as I mentioned before, it is an active sensor. Lidars operate by sending out a beam of light and using information from that reflection of the light to learn about the distance or composition of the target. Here you can see an example of information gained from a Lidar sensor. In this example, a Lidar was most likely placed on the bottom of a plane and flown by the Capitol. The main idea behind the operation of a Lidar sensor is the range equation. The range equation states that the distance of the target is equal to the speed of light times the time it takes to get the emitted light back divided by 2. The division by 2 is to take into account that the light has to travel twice as far as the distance of the target, because it goes both towards the target and back from the target. This project isn't exactly using Lidar, but it is similar in that it is using the reflection of a laser to gain information about the distance of a target. Computer vision is basically gaining information from images. This project uses OpenCV, which is an open source computer vision library. Here you can see the Lidar sensor used during the scanning. All components were attached to a 3D printed rigid mount. On the right side of the sensor is the line laser, which is the transmitter of the system. When powered from the connected Arduino, the laser emits a red line. On the opposite side of the mount is the Raspberry Pi camera, which is the receiver of the system. This camera and the connected Raspberry Pi together create the data acquisition system, which utilizes computer vision techniques to detect the location of the laser beam as it scatters off the target. The receiver and the transmitter are 12 inches apart, an important aspect of the sensor which will be explained later. Finally, on the upper right side you can see an attached piece of tripod. During scanning, the mount was placed vertically on top of the tripod so it could be pointed at various angles. The target I chose for this assignment is the well outside of Rossborough Inn, shown on the left side of the screen. On the right side of the screen, you can see the well's location marked with a star. The well is located outside of Rossborough Inn near Route 1 and across from Ritchie Coliseum. I chose this target because I thought it was a unique piece on campus that not many people know exists. Also, I thought it was a good target to scan because most of it is not too dark or reflective, and there is space around all 4 sides to place the Lidar during the scanning. This project relies on the geometry between the camera and laser. As shown by the triangle above, the camera view diverges. With the configuration shown where the laser is to the left of the camera, as the target moves closer, it appears to be moving left in the camera screen. As a result, looking at the X value of the pixels reflected by the target, you can calculate how far away the target is from the camera. Before any target scanning could be done, the laser first had to be calibrated. First, a single beam laser was calibrated. The setup for that calibration is shown here. You can see the laser, Raspberry Pi, measuring tape, and computer screen. During the scanning, the lights were turned off so the camera could better see the green laser. To do the calibration, a paper was moved from 1 foot in front of the camera to 9 feet in front of the camera in 6-inch increments. The data acquisition system uses computer vision algorithms to detect the location of the laser beam as it reflects off the target. For each frame, the DAC applies a color mask and then finds the minimum and closing circle and centroid. The goal of calibration was to find the correct RO and RPC values. RO compensates for the alignment errors, while RPC is based on the radians per pixel pitch. The XY coordinates found in the camera image were used to find a range measurement based on the sensor geometry. These range values are the red curve shown. The blue curve is the theoretical values, and the two curves best matched when the RO value was 0.1 and RPC value is 0.00. The next step after calibrating the single beam laser was to calibrate the line laser. Here you can see the red line laser. The line laser was aligned so that it showed up as a vertical line in the screen parallel to all the green lines. Similar to how the single beam laser was aligned, this laser is moved from about 1 foot to 9 feet in 6-inch increments. This video shows part of the calibration process. You can see the red line starts towards the middle and moves towards the left as the distance to the target increases. For the line laser, the theoretical values best matched with the measured values for an RO value of 0.092 and RPC value of 0.01. This image shows the setup for data collection. The line laser is powered by an Arduino which, along with the Raspberry Pi, was powered by a battery pack. The Raspberry Pi was connected to a laptop through VNC over Ethernet. During scanning, the angle of the laser was measured by an iPhone attached to the mount. The entirety of the well was imaged with 8 scans, one on each side and one on each corner. This image shows one of the side scans. To get the laser high enough, it was placed on top of a table. This image shows the placement of the laser for one of the corner scans. It was placed on the ground since the main aim was to get the corner portion of the brick base. Scanning was done by changing the angle of the laser in small increments and recording an image in the angle at each point. There were several challenges during the scanning process. One challenge was the height of the target. This was addressed by putting the tripod on top of a table during scanning. Another challenge was the nearby lights. It ended up that the best time to scan one part of the well was right before sunset when it was pretty dark, but all the bright lights hadn't turned on yet. Finally, the ground next to one of the sides of the well was slanted. This was compensated for during the 3D point cloud processing by rotating the point cloud. Here are some of the images taken during the scanning. You can see the red laser line on the left side of the image and the angle it was taken at in the top right corner. This program converts the images to the XYZ point cloud coordinates. You can see on the bottom each image that is being processed. It starts off by defining the laser parameters found during calibration, and then imports all the images taken during the scanning. It then manipulated the image so it can pull out the location of the red line. Using information about the location of the pixels of the line and the angle that each specific image was taken at, it then calculates the 3D coordinate for each point along the line. All this information is then written into a text file. The following images illustrate the processing done in the previous Python program. First, here's an example of one of the unprocessed images. The next step was to black out the right side of the image, as shown here. And next, the image was blurred. Then it was converted to the HSV color space. And finally, a red mask was applied. And now the location of the laser pixels can easily be distinguished from the rest of the image. This is an example of one of the output text files, and you can see there are 3 columns for X, Y, and Z. Here's an example of the 3D point cloud of one of the side scans after it's been slightly post-processed. And here's an example of one of the corner scans after it's been slightly post-processed. There were 3 types of functions applied during the post-processing. The first was rotation. I wrote a function that took in the 2 axes that needed to be rotated and the degree to rotate them. Next, there was translation, where a shift value is added to the X, Y, or Z axis as necessary. And finally, there was noise removal, where data points outside of the well were removed. Here you can see one of the corner scans being combined with the other scans for the well. The new point cloud is first rotated, then translated, then has noise removed. And here is the final side scan being added to the rest of the well. The final point cloud represents reality fairly well. you can see the 4 sides of the well and the 4 flattened corners of the brick base. You can also see the top part of the well and how it is at a slant. I did a comparison between the size of the point cloud and the size of the well. Here are the two sizes for the height of the brick base. Both are around 3 feet, but the point cloud one is a little larger. I also measured the height from the ground to the bottom of the roof. Again, both are pretty similar in about 8 feet. The final major measurement I compared was the width of the well. Out of all the measurements, this was the most consistent, around 5 feet 4 inches. And here's the point cloud superimposed on top of the image of the well. The conversion from 3D point cloud to mesh was done in Cloud Compare. Here you can see the imported 3D point cloud. The next step was to compute the normals. And then do the Poisson surface reconstruction. And here's the final mesh.